Good morning, everybody. So today there's a Codeforces round, in particular round 717. I'll let you look at it right here while I talk. So we'll be doing that, and I'm a minute late, so I guess we'll jump in here. Let it load. But before we start, I've got a couple announcements. So first, am I not registered? I'm not registered. All right, well, then I guess not too big of an issue. First, I was doing Kotlin for a few contests, and I think that's a good idea. I'm still going to do Kotlin in some of my free time, but I think as far as me helping other people, I feel like I can do a lot more good in Java than in Kotlin, just because there isn't really, there aren't a bunch of people who want to use Kotlin and don't know where to look, and most people who know Kotlin learned Java to begin with. So I feel like just at least for things where other people are seeing me using Java is a good idea. And also, since I'm going to be using Java for World Finals, and that's what I'm going to be doing in like Code Jam, Google Code Jam, and like Div 1 rounds, kind of makes sense to just be consistent across the board. So I think we're going to do that. That's the first announcement. Next, what else? This weekend, there's this thing called Ludum Dare. And you go to ldjam.com if you're interested. This is a competition. It's a 48-hour contest. So you have 48 hours in order to make a video game from scratch. If you've never done it before, this is a great place to start. I did a bunch of these a long time ago when I was first learning how to program, and it really helps with your implementation skills. So if you struggle implementing hard problems and like doing stuff without bugs, doing like writing a bunch of code in a short amount of time under a lot of pressure is a great way of doing that. And I think this is a super fun contest, so I'm going to be doing that. Uh-oh, Zero has issues. So yeah, there we go. Awesome. So announcements are done. On to the contest. Tit for tat. And let me go turn off Zero. We have company?
Understood, sir.
All right. Given an array, sorry about that. I am so unprofessional. Given an array of length n, you can do at most k operations of the following type on it. Choose two different elements in the array, add one to the first, subtract one from the second. However, all the elements of A have to remain non-negative after this operation. What's the lexigraphically smallest array you can obtain? Add one to the first, subtract one from the second. So you can do one operation, subtract one from this, add one to this. Add one to this, rather, yeah. So you always subtract one from the first element. Thank you, Zero. I am so unprofessional. Anyway, okay, two different elements. Add one to the first, subtract one to the second. Yeah. So you always and you can do at most k or exactly k, most k. So you always subtract from the first element and always add to the last element. Yeah, 0, 1. Yeah. Okay. Sounds good. Should be pretty easy. Here we go. Okay, so each element's up to 100. There are 20 test cases. Make a priority queue, integer queue. Well, let's just read the array. So int n equals this. Sorry, next int. And then k will be the integer after that. All right, and then we read in the array. So that's n. We go through the array. Yeah. So if a at I is greater than 0 and k is greater than 0, then k minus minus, a at I minus minus, a at n minus 1 plus plus. And then we're done. Okay, cool. So then, I guess this is just a while loop. And then for I and a, this out I plus a space, and put a new line. So that should be all we need for problem A. Two 21501. Okay, looks good. Let's submit it. Can't submit. On to problem B then. I forgot. All right. AGA XOR. Baby Ehab is best known for his love of certain operation. Well, let's try again. Baby Ehab is known for his love of a certain operation. Okay. He has an array of length n and decided to keep doing the following operation on it. He picks two adjacent elements, removes them, and replaces a single integer in their place with their bitwise XOR. Note that the length of the array decreases by 1. Now he asks you if you can make all of the elements in the array equal. He requires that you leave at least 2 elements remaining. Yeah, so you want to see if there's any index where the prefix XOR is equal to the suffix XOR. In other words, if the prefix XOR, well, the XOR of the entire array needs to be 0, right? Yeah. The XOR of the entire array is 0. You can always just choose the first element and everything else. Should be a banger. Ends at least 2. Yeah, okay. I think that's it, right? So if the XOR is 0, then we're good. Otherwise, we're not good. Okay, yeah. Oh, wait. It's not necessarily the case. It might be more difficult than that. If you have 3, 3, 3, for instance, that is possible. Good. Okay. Yeah. So the size of the array might be, you might split it into 2 groups. You might also split it into 3 groups. But you'll never split it into 4 or more groups. Okay. Otherwise, I will be the first split point. So int pre XOR equals a at 0, and then pre XOR we want to add a at I after we consider I. Okay, int mid XOR equals a at I. Mid XOR we want to remove A at I here. And last XOR equals A at J. Start I plus 2 here. So we have the last XOR. All right, so then in this case, we want to add, okay, well, yeah, subtract it here. So then we need to add, or we need to remove from last XOR. This J is about to get incremented. And then we need to add to mid XOR. All right, so here's where we check. So if pre-XOR is equal to the mid XOR and mid XOR is equal to the last XOR, then sys out yes and return. Oh, sys out no. We don't actually need last XOR, we just need and mid XOR is equal to the X of everything. Be yeah, okay, I think this is right. This should be, yeah, J is not included. Okay, I think this is fine. Oh, continue outer. All right, so we should be able to register now. Let's do that. Submit to A. And then also submit to B. Got A. So we'll read C. Wrong answer, test 4. Okay, so likely due to how this is happening. All right, prefix XOR is the first element. The mid XOR, so we have so we've got some stuff, then we have I, and then we have some more stuff, and then we have J, and then some more stuff. If the XOR is 0, it's always possible. Yeah, that's true. If the XOR isn't 0, it might be possible. You can get 3 or more groups together. If it's 4 groups, you can just combine the last 3 groups. If it's 5 groups, you can also combine the last 3 groups. Or the last 2 groups. 4 groups, you combine the last 3 groups into 1, yeah. So you can remove the last 2 groups. Okay, so I starts at 1, J starts at I plus 1. The mid XOR starts at A at mid XOR is A at I initially. We brute force how much to take. Can we print in any case? Because if that's not a bug, then this should be yes, rather than the other yes. We'll read C. Baby Ehab was toying around with arrays. He has an array A of length n and defines an array to be good if there's no way to partition it into two subsequences. So the sum of the elements in the first is equal to the sum of the elements in the second. Now he wants to remove the minimum number of elements in A. So it's good if there's no way to do that. Okay. He wants to remove the minimum number of elements so that it becomes a good array. Can you help him? Okay, so what makes an array good? If you can, the indices. So you can always just make it size 1, so it's always possible. Is the answer ever bigger than 1? Let's think about that. So if you have like 4 3s, that means this sum is equal to this sum. The checker is case insensitive. Okay. Interesting. So that means we're just wrong in another way on B. Okay, so yeah, let's say this is the case. Are all of the elements at least, they are all at least 1. So yeah, if you can split it, there's only one way of splitting it, which means if you remove any element in the first position, that might not be the case. So if you have 3, 10, let's do something simpler. So 1 here, and then let's say this is a 1 and this is a 2, and this is also a 2. So initially the way to split it is that. But then we have an issue here, which is if you remove this, then you can split it here. What if we remove the smallest element in the array? So you have a split point. If you remove the minimum element, then you want to shift this over by the minimum element over 2. Yeah. So just find any minimum and then remove it. And that works. Okay. So we'll do this first because that's easy. Easy mode. and then figure out why we're wrong for B. Nice and small bounds too. A subsequence. Oh, never mind. We're totally wrong. Okay. So a subsequence can be obtained by deleting some elements of the array. So that's a subsequence. Or that's a subsequence. We want a subarray. We can do it with a subarray. So the answer might be pretty big, right? Or is it? Okay, let's go back to this. There's a necessary change in test, so rejudge is there. All right. Man, geothermal's crushing us. Why are we wrong for B? The XOR of everything is equal to 0. The answer is yes. Yeah, that's right. Okay. Otherwise, the prefix XOR starts at A at 0. Then we look at each thing here. Let's get a code for what we submitted, maybe. Oh, yeah, this isn't right. Mid XOR has a bunch of stuff in it that we don't delete at the end here. Yeah, when we go through this like the second time, we want to delete all of the things after this. So this is what we want to submit. Let's just print the capital yes just in case. Okay. Man. Notifications. So many notifications. Okay. Alright, we got it. Let's think about this. So, yeah, first question is subset sum, right? Can you partition all of the elements into, or can you find some of the elements that sum to half of the sum? So I think you might just need a DP for that. Oh, can we do something with parity? hold on a minute. Let's say the sum is even. Like if the sum is odd, it's going to be impossible. Yeah. So if the sum is even, then you split it into two halves, which are both not necessarily odd. Half of an even number can be even. Yeah, okay. So these could both be even. Never mind. Okay, so that is not what I'm looking for. Can you divide all numbers by 2? You should be able to divide every number by 2. Yeah, if you divide everything by 2, it's just you double the size of your unit. Yeah, okay. So divide out powers of 2. So here's the thing now. So initially the sum has to be even. Which doesn't really mean much, but there's at least one odd number. Or yeah, there's at least one odd number. If we remove that, then the sum becomes odd, so it'll be impossible. So we can do that, and then for the initial part, we just need to see which sums we can hit with knapsack. All right. So, single test case, very easy. Int n equals this. Int array a, read array size n. Boolean array can reach. Equals new Boolean array size. How big does this need to be? 2000, 2001 times 100. So for each thing we can buy, we want to go in decreasing order. So if not can reach at 2, then continue. Otherwise can reach at 2 plus cost equals true. So our runtime here is 10 to the 5th, like 2 times 10 to the 7. I think should be fine. It's very, very fast operations. Okay, once we have that, we want to say, oh, I guess we need the sum. All right, so now we have the sum of everything here. So if can reach at sum over 2 and sum mod 2 is equal to 0, this is the case, print oh yeah, I guess if this isn't the case, so if we can't reach this or sum over 2 is not equal to 0, then sys out 0 and then return. Okay. Otherwise there is some way of doing it for 1, so now we need the smallest bit. sorry, math.min, whichever has the fewest trailing zeros, or integer.number of trailing zeros, and I. Cool, cool. Yeah, we should be fine there. So then for so we look through each thing. So now we want to say if a at I modulo 2 to the trailing zeros plus 1 is not equal to 0, then ans equals I. That's it. That easy. Index 3. Okay. Yep, that's the last odd number, so that works. There we go. All right, cool. Under problem D. This time, baby Ehab will only cut and not stick. He starts with a piece of paper with an array A of length n written on it. He does the following. We got it, by the way. He picks a range L to R and cuts the subsegment A at L to A at R, removing the rest of the array. He will then cut this range into multiple subranges. To add number theory spice to it, he requires that the elements of every subarray must have their product equal to their LCM. In other words, the GCD of every subarray has to be 1. Okay, but what's happening here? He starts with an array of paper, length n, picks some range and cuts it out. Oh, and he removes the rest of the array. Alright, he partitions this into continuous subarrays, such that the product of every subarray is equal to the LCM. Now for Q independent ranges, tell him the minimum number of subarray he needs. Let's look at an example. I don't think this is a very well written problem, but okay, I think it's fine. He will pick a range and cut the subsegment this, removing the rest of the array. He then cuts this range into multiple subranges. He requires that the elements of every sub-range must have their product equal to their LCM. What? This doesn't make sense. I'm very confused. He partitions the elements of this into continuous subarrays such that the product of every subarray is equal to its LCM. Oh, this is a query. Okay, he gives us a query And then we need to partition it. Gotcha. Okay. All right, so the query is from 1 to 6. 1 to 6. Okay. So let's look at this again. 2, 3, 10, 7. 2, 3, 10, 7, 5, and 14. So that's the first query. What's the second query? Two to 4. 2, 3, 4. Oh, that's not. I've got my indices wrong. 2, 3, 4 like this. So you're good. Okay, yep. And then 3 to 5. So this is 3 to 5, so you need to cut it here. Okay. Yeah, okay, so we need to figure out for each index what's the next thing it shares a factor with. Are all of our numbers small? They are. Nice. We can prime factorize everything. Should be easy. So we find the next thing it shares a factor with. And then we do binary lifting. I think. Yep. Yeah, so we find the next thing everyone shares a factor with. Then we have to be a little careful for this. This is to the end. Oh, I guess, yeah, so we're saying if you start here, where do you end? Yeah. Yeah, so if you start at the 10, where do you end? So we can do that going backwards. Find lift at 0, and then we can find the number of things we need to lift by. All right, so binary lifting, cool. Very good. Am I too big? I'm way too big. Why am I so big? Sorry about that. Apologies. Let's solve D here. Okay, so a couple things that are required. First thing is prime factorizing. So we're going to need a pre-comp method. All right, so then static int array factor of static boolean array is prime. Yeah. I guess we can just use factor for that. Okay, so start off by doing our pre-comp. And then we will worry about this in a bit. Okay, factor of. So for int I equals 2 less than factor of length I plus plus. If factor of at I is equal to 0, Well, if it's not equal to 0, then continue, because we know it's not prime. So otherwise it is prime. So for in j equals I guess j is less than factor of dot length j plus equals I. In this case, we want to set factor of j equals I. So for each of these things, mark one of their factors as I. Yeah, I think this is what we're looking for, so we should be good there. Okay. Cool. So now we have factors of every number. So now we want to say static array list integer prime facts of some integer n. Then we want to return this thing at the end. So now, while n is not equal to 1, to return dot add. I guess we should probably make this just a hash set or a tree set, maybe. I guess let's make it a hash set. It's faster. Or no, we can just do array list and then just be careful here. Okay. Yeah. So to return dot add factor of n while so we add this factor, and then we remove this factor from n. We return the list of factors we have at the end. Good. Okay. Yep. Sounds good. So we want to see, is this multi-test case or single test case? One test case. Very nice. So we need an array next. It's a new int array of size n. We're going to build this here. We should be good to go here. All right, so we're going to do this with a sweep. So for int at, we'll start at the end of the array, go to the beginning, and we want to say if, or we want to first get all of the indices this hits. So int next end, this will be where we would otherwise end. That'll be n. And next next it at equals next end. We want to get our list of factors. We also want int array next scene some new int array of 10 to the 6. And then fill it with n initially. So we get prime factors of this thing. Then for int I in factors, we want to say for each of these, next end equals math.min of next end and next scene at I. Okay, and then for and I in factors. Next seen at I equals at. Okay, so now we have the next time we see each factor, which we'll read in a future loop, and then we can see what the like limit for each thing is. Okay, so now we need our lifting table. So we need int double array lift, so new int array, it'll be n, I guess it'll be 20 by n. Lift at 0 equals next. Int exponent from 1 less than 20 plus. I equals 0 less than n, I plus plus. If lift at e minus 1 I is not equal to n, then lift at e I equals lift at e minus 1, lift at e minus 1 I. So we go up this much, we go up e minus 1, and then we go up that much again. All right, very good. Cool, so now we need our print writer. To answer each query, we need an L and an R. Okay. So now, yeah, so what do we need to store here? The total number of moves, or total cuts. So, well, lift at L is less than or equal to R. We want to do this. Okay. Int max lift equals 19. I guess this is next. So next at L. Well, lift at max lift L is greater than R max lift minus minus. Okay, so now we know it's not greater than R, so we have to take this many steps. So total cuts plus equals 2 to the max lift, and then we want to say L equals lift at max lift. Sorry, yeah, lift at max lift L. There you go. I think that should be it. Does this work? How much time do we have? We're running low on time. We might not solve set. It's a bit concerning. All right, let's print this array. Two, 4, 4, 5, 6, 6. Okay, so this is 6. Yep, this is also 6. Oh, this one should be 6. Or this should be 5, yeah, okay. 10 should be 4. The 3, I guess, should also be 4, right? So if you start here, this is the next place you cut, the 2 should be 2. So next is right. All right, cool. Lift looks right. Let's see. Okay, otherwise, so this is where we're getting stuck, I think. Yes, minus 1. Nope. Okay. 0 to 5. Oh, I guess otherwise. Two, 0, 1. The number of sections, right? So this plus 1. Looks good. It's going to be close. Assuming we even got that. So read while we listen for CF notifications to give us our answer. This time around, baby Ehab, all right, we got it. Baby Ehab will play with permutations. He has n cubes arranged in a row, numbered 1 to n. He'll make exactly j operations. In each operation, he'll pick 2 cubes, switch their positions. He's wondering how many different sequences of cubes can he have at the end? He's a turbulent person. Wait, what? You can have any sequence, right? Oh, exactly j operations. Okay. He's a turbulent person. He doesn't know how many operations he'll make. So he wants the answer for every j between 1 and k. Oh, you've got lots of cubes. Okay, interesting. Interesting. So initially, we have n minus 1 choices, right? You've got, let's say you have 5 cubes, so you have n minus 1 choices. After that, you have some other number of choices. So you can have 2 inversions, or you can have 0 inversions. Yeah. Otherwise, if you have, that's on 2 turns. So initially you have 0 inversions, and that's one way. Then you have 1 inversion. There are, of course, n minus 1 ways of doing that. How many ways are there to have 2 inversions? Alright, Geeks for Geeks. Are you going to give me an m factorial? Okay, nope, unhelpful. Thank you. There you go. All right, this looks like what we want. Whoa. Okay. So this is the solution to the problem right here. Should we read it or look for a better solution? This is annoying. This is on OEIS. Okay, T and K is the number of permutations with K inversions. The nth row gives a growth series with respect to transpositions. Having disorder equal to K. Yep. Is there a way of generating this? That doesn't seem right. Formula? Okay, this looks like a DP. Yeah, so I think this is going to be Matrix Expo, unfortunately. Is that the thing we were looking at previously? There's no way of getting around the Matrix Expo. Yeah, n squared dp. Yeah, okay, so the solution is just do this, but with Matrix Expo. Ugh, it's disgusting. It's absolutely disgusting. It's disgusting, it's unhelpful, I don't feel like doing it. Okay, fine, I guess, right? That's what we read here. It's like, and you can do this in m squared with a... Yeah, okay. So we do the DP, we can pre-compute this thing, we don't have to worry about the complex stuff, and then we're set. Alright, what's this DP? yeah, let's just read it, I guess. Let's learn. So dp n by k states. So there are this many okay. So we just like look at which element we're about to place. Yeah. So if you have a bunch of like elements here, you can either place a 1, in which case you have n minus 1 elements left, and you want k inversions. Or you can place like any number of elements here. So you can place, or I guess, you're always going to have n minus 1 elements left. The element you place here, you have n minus like x, or you have k minus x inversions left. And yeah. So this element is always less than or equal to m. So we're set. Okay. So that's a solution. Is it one query? Yeah, one query. Okay. All right. Fine. We can do it. So let's do our static long add long a long b return a plus b under mod static long mod equals 10 to the 9 plus 7 static long sub long a long b return a minus b mod plus mod static long multiply long a and b all right, add, subtract, multiply. I don't think we need division. We do need matrix multiply though, right? Static long double array multiply long a long b. Okay, how do you multiply two matrices? I'm gonna be a fool here. You know, this is the kind of thing that you learn in high school and then you just never use unless you're a math major, because it's just not helpful. Okay, it's always so easy to mess up. So you have, this one is n by m. This is by an m by like p. This yields an n by p. Okay, so what does this mean? This means this has to be equal to this, because we lose it. So that is the number of columns. So the height of this has to be equal to the width of this. So we pick this column and this row. Is that right? So we wait, the second number of rows, number of columns. Nope, the number of columns. So the number, yeah, this is the number of columns. This is the width. Okay, so the width has to be equal to the height. So you multiply this by this, and that will give you this space here. I think I'm right there. I think that makes sense. So yeah. Okay. So if a dot or a at 0 dot length is not equal to b dot length, then is null. guess we don't need this. Okay, so we just need to say C at ij equals add C at ij. We want to multiply A at ik by B at kj. Turn C. I think that's how you multiply two matrices. Okay, who really knows though, am I right? So how do we do this matrix multiplication? So what does this mean? We have some array, or we have some matrix. This is like some transformation matrix along A. So this is, yeah, this is like dp of like each way. So this is, we have 200 inversions, 199, all the way down to 0. And this needs to give us a dp of the same thing, 200, 199, all the way down to 0. But this is for, this is dpn, this is dpn minus 1. So how do we do this? So 200 will be equal to this thing times this. So dp of 200 is equal to just dp at 200, so this is a 1. dp at 199 is equal to, you can do 200, or you could do 199. Yes, it's these two, I think. Yeah. This is these ones, so I think it's just a diagonal. All right, so what do we need? We have the number of cubes and then k. Oh, we also need fast exponentiation. Well, maybe we don't. Yeah, let's just not do that. Okay, let's just do it in here. So the matrix that we're interested in, I guess this is the move 1. This will be k by k. So we have ones along the bottom diagonal. This is the row when the column, oh, I guess this is not how it works. Okay, j equals 0, j is less than or equal to I. So that's the bottom diagonal. Okay, bottom left diagonal. Yeah, all right, cool. So that's move 1. So now we need the lift. Exponent equals 1, e less than 30, e plus plus, move lift at e equals multiply. What's wrong with this? That's fine. Oh, it's triple array. Multiply move lift at e minus 1 by move lift at e minus 1. Okay, we've got that. What else? So for every right parity of inversions, yeah. So for int n inversions equals k, n inversions is greater than or equal to 0, inversions minus equals 2. Because you can waste two things. Yeah. Awesome, and then sys out the ants. So now we just have to calculate it for this one step. So we need the long start. Oh, I guess we can just, yeah, we can just do this. Cool. That's pretty neat. Okay, start equals new long, k big. Oh, I guess it's going to be k plus 1, huh? Yeah, so this is always plus 1. Equal to k plus 1. Okay, so it's, or I guess it's going to be how many rows? K plus 1 rows, 1 column. So now start at n inversions, 0 equals 1, otherwise it's going to be 0. So there's one way to start with each of those inversions. Then we want to say for int I equals 0, I is less than 30, I plus plus, if n and 2 to the I is not equal to 0, then start equals multiply move lift at I by start, then print start at 0. All right, start at, yeah, start at 0, 0. Oh, we have to do it separately. Never mind. Okay. Oh, we have to do this with I operations. Okay. Yeah, so for int have equals 0, have is less than or equal to k, have plus plus. Have and inversions greater than 0. Zero, 1, 1. So when have is equal to 1, we print 0. Okay, we should probably make a method to print a matrix. should do this. Yeah. That looks right. This is not right. Have is 1. So you can swap, wait. So you can get 0 swaps, yeah, okay. So after 1 swap, the answer is this. Okay, I think I had this right initially. So j equals I, j is less than k. So we want the upper diagonal. There are 2 ways of doing it. So our matrix looks like this. We have 0, 1, 0, 0. So we have 1 inversion. What should this go to? So we have 1 element. Okay, now we're going to place our second element. So how many ways are there to have 1 inversion? There's just the 1. How many ways are there to have 0 inversions? Oh, there's the 1, of course. We would place a smaller number here. If we want 1 inversion, there's 1. There's 0 ways to do this, 0 ways to do that. So this 0 should be the sum of everything. Why is this a 2? Oh, this should be n minus 1. Initially it looks like that. Okay, good. Yeah, you can't actually have 3 inversions, I guess. Is that the case? Yeah, equals. Oh, is this going to get messy? Do we have to do the naive DP if it's less than 200? Okay, well, we're going to get the problem eventually. Yeah, that's kind of annoying. So what I'm saying is, like, you could place a very big number at the end. If you have one item left, you can't make an inversion there. Oh, that's kind of annoying. All right, static long dp. All right, is there a better way of doing this? I don't know, maybe I should just read the existing documentation on it. Yeah, this isn't usually in this state. By 300. All right, so this is all -1s. If that's not -1, then return it. Otherwise, so long to create here equals 0, or I guess this is just the answer. Then return dp at n left and inversions equals the answer. So for int to skip equals 0, skip is less than math.min of n left, less than or equal to math.min of n left, and n inversions to skip plus plus. Okay, in this case, go, or I guess ants equals add, ants go n left minus 1, and inversions minus to skip. Alright, so we need a static. Alright, yeah. So if n inversions is greater than n left, or I guess if if n left is greater than 250, then we need to do some magic here. Okay. We'll do some stuff here. Okay. How many inversions are there? There are k inversions. All right. So this is inversions. We can place any number of these things here. Or wait, we just want, yeah, this isn't right. So this needs to be another for loop. Okay. All right, so int actually have equals have actually have is greater than or equal to 0, have minus equals 2, ants equals add to go. If we have n things, this is how many inversions we actually have. Okay. You can speed this up if we need to, but I don't think that'll be the issue. Okay, we go through each of our powers of 2. If n left, okay, so this is like the skip. So int n skip will be n left minus 250. N skip did it, then we do this. Okay. So now we have the number of ways of doing each number of inversions after a huge number of steps. Gotcha. So we've skipped this many. Okay. Yeah. So long ans equals 0, return the answer. So the number left will be, this isn't true, so start at n inversions is equal to 1. Yeah. So left equals, or I guess int inversions remaining. This is equal to 0. Inversions remaining is less than n inversions. Inversions remaining plus plus. Ants equals add. Go with how many are left. So n left minus to skip. Inversions remaining. This times, or do we want to multiply it by start at inversions remaining 0. Range extended bounds exception at -1. Oh, I guess if n left is equal to 0, return 1. Nope. Nope, nope, nope. There are 4 ways to do 3 inversions. Is that what you're telling me? Oh, this needs to be n left minus 1. If you have 2 things left, you can place a 0 or a 1 here. Yeah, okay. If there's 1 inversion and 3 things, oh, or these cubes aren't adjacent. Oh my goodness. Can they be the same cube? Totally misunderstood the problem. If n cubes in a row, 1 to n. So you have 2 cubes. Oh, you have 3 cubes. Okay. There are 3 pairs of cubes you can swap. So the number of inversions is not important at all. So this is, yeah, this whole solution is kind of just unhelpful. All right, well that's why you don't solve the wrong problem, I guess. Can we figure it out in 20 minutes? We can give it a shot. Can you ever have an odd number of numbers be in the wrong position? So yeah, if you have an even number of numbers in the wrong position, you have like that many moves over 2, I guess, right? Or maybe not. So if you have like 1, 2, and 3, if you swap 1 and 2, then you have 2, 1, 3, okay? And then you swap 1 and 3, then you have then you can have 3, 1, 2. So a cycle of length 3 takes 2 swaps. Yeah. So yeah. Okay, permutation. Like you can pick a cycle in the permutation that takes n minus 1 swaps. The question is, how many arrays can you make at the end? There are going to be multiple different ways of making the same array, which is tricky. Interesting. All right, I'll be right back. I think all the cycles you pick have to be distinct. So when you pick a cycle, you've got like n choices for the first, n minus 1 for the second. And then you divide by the cycle size. Yeah, for 2, because it's a cycle size, not because it's 2 factorial. So you divide by 2, not 2 factorial. So if it was 3, it'd be n times n minus 1 times n minus 2 divided by 3, not divided by 6. So yeah, you pick this distinct cycle. The cost of doing that is n plus 1. Or yeah, the cost of doing that is n minus 1. To pick a cycle of that size, then you get another dp value. So you can do a dp where your state is the number of things you've used and how many k you have left. Then you have an order k transition. I think we can do that. Let's make a copy of this. I love how we just spent an hour solving a problem that wasn't part of the set. You know? Anyway. Alright, so this is a dp. We'll keep the dp actually. Probably keep n and k. We don't need anything else. So int n used, and then int n versions. Okay. If dp at n used and inversions is not equal to -1, turn dp at n used n inversions. Oh, do we need the cycle size too? Yeah, because we need to pick the cycle size in decreasing order. Yep, okay. If the cycle size is equal to 201, then return 1. I guess we'll say there's one way of doing it. Let's see what the answer. Okay, so otherwise we need to figure out how many ways there are to take this. So we can either take 1 or take none. I guess we have to take all of them at once, right? So n factorial, n minus 1 factorial, n minus 2 or n minus 2, yeah, okay. Okay, so for int n cycles to take equals 1, n cycles to take times cycle size is less than or equal to n used. Or I guess what is this? This is n moves, I guess. times cycle size minus 1 less than or equal to n used n cycles to take plus plus. Alright. Gotcha. Okay, so we know how many cycles we're going to take. Oh, we need factorials. We also need division. We also need fast pow. Ah, okay. Static long fast pow, long base, long exponent. If exponent is equal to 0, return 1. Turn multiply the base to the wait, hang on a minute. How am I going to get n factorial? Okay. This is dumb though. We want naive and choose k. Alright, so yeah. This will be answer times n minus I ans equals multiply answer by factorial or by mod inverse of I. And then return answer. Okay, good. So, yeah. All right, so we have that. Good, 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 good. This isn't n choose k though. We just want this part of it. Yeah. Those things. All right. In this case, we want ants 6 minutes. Oh no. Okay. So ants equals add ants to what are we going to take? So cycles to take so go n used minus cycles to take times cycle size. how many moves, n moves minus number of cycles we have times cycle size. All right. Good. Okay. Long next ways equals go. What is this thing? And then we want to multiply this to the current ways. It's going to be n choose k divided by, or times mod inverse of fast pow of cycle size to the n cycles to take okay, what is this n choose k? So we want the n will be n minus n used, and then we choose, we keep multiplying down to n minus n used minus n cycles to take times cycle size. So this is maybe right, but I got a lot of work to do here. You can skip you can skip any even number. Okay. If I get this, that would be absolutely insane. Oh, come on. Oh, array index out of bounds. Okay, yeah. So some math debugging to go here. All right. Well, yeah, I can explain solutions, I guess. Then. Oh well. All right. Yeah. GG to everyone who beat me. Probably lots of people, honestly. Yeah. Quite a few people. So GG to them. Nice job, Monogon and Geothermal and Anton for solving set. I guess it was a div 2, so I guess maybe a little bit less special, but still good. Let's go over solutions. So I guess we'll probably do solutions to all problems because I've got a good idea of how to do all of them at least. So for tit for tat, let's talk about it. So you have an array of length n. You can do at most k operations, and each operation is you pick 2 elements, add 1 to the first, subtract 1 to the second. You want the lexicographically smallest array that you can get. So what you should notice here is, since you want to make something lexicographically smaller, you want the first element to be as small as possible. If that's the same, you want the second element to be as small as possible. If that's the same, so on, all the way up to the last, which you want to be as small as possible. So if you're going to have to add 1 to some number, you might as well add all of your values to the last number. And then, yeah, I guess there's that. So add everything to the last number, which basically means you can subtract up to k from as many numbers as you want. And you obviously want to subtract from the beginning, if possible. So you keep just subtracting from the first one, and then from the second and third, and so on, and then you add to the last number. Yeah, that's the idea. There are a bunch of ways of implementing it, but basically you just k times want to subtract from the first thing you can, and then you add to the last number. My code that does that looks like this. So I have my array, and I go through the entire array. Well, this number is bigger than 0, and I can subtract 1 from it. I do subtract 1 from it, and then I add 1 to the last number. If the array is all zeros, this should be fine still, right? So like if we have one test case with 2 numbers, do 2 operations, 0, 0, it'll just exit this for loop early. Cool. So yeah, that's problem A. Pretty simple. That's the idea. Hopefully that proof made sense. For problem B, this one's a really interesting problem, I thought. I think you can probably do it with higher bounds, but the idea was interesting, and you don't really need bigger bounds to make it cool. But the problem is EHAB is known for loving bitwise XOR being the same for all elements in some array. So if you have your array, which maybe it looks like 1, 2, 1, 2, 3, 3. Maybe this is your array. What you can do is take any 2 adjacent elements and then merge them into 1 element. So you can pick these 2 and the 1, and after you merge it, all the 3's will stay the same, but these turn into their XOR. So the XOR of 2 and 1 is 3. In binary, those numbers are 0, 1, and 1, 0. You do XOR by checking if there is an odd number of rows in each column. If there are an odd number of rows in both columns, so we put a 1. If there are an even number of 1s in a column, you put a 0. So that's XOR. So yeah, if you write each of these in binary, you get the numbers 0, 1, and then 1, 0. The XOR will be 3. So your array looks like this. After you merge these 2, you have all 3's. And in this case, the array consists of at least 2 numbers, and all of the numbers are the same. So this is what we're going for. So in this case, the answer is yes, it is possible. Now, it's not always like this. There are also, what if you have an array with 4 3's? Well, if that's the case, you could split it up like this. Right? You could have just the first element and the last 3 elements. One thing to keep in mind that's helpful a lot of the time in competitive programming when you're working with XOR is if you have 2 of the same number, their XOR is equal to 0, so they cancel each other out basically. So if you have 4, if you have greater than or equal to 4 of the same element, then you can always subtract 2 from those, right? So you can wind up with either 3 or 2 of the element that you're trying to make. Now let's look at this 2 case. So if 2 elements have the same value, that basically just means the entire XOR, or the entire array, has an XOR equal to 0, right? If you think about it, if they're the same value, they'll cancel out, which means there's some prefix, right, whose XOR is equal to the suffix. But that means that the XOR of the entire array is 0. So in that case, it doesn't even matter where you split. You can split anywhere, and it'll still work. So that's the first case. The second case is this 3, well, if you have 3 of the elements remaining, which is a bit more tricky. But in that case, you have some elements here. You're going to have some range in the middle, and you want to see, is there any range in the middle? It has the same XOR as the prefix and as the suffix. It might be a bit easier to think, is there any range in the middle where the XOR here is equal to the prefix and also equal to the XOR of the entire array? Those are equivalent statements. You can check the XOR of the entire array and the XOR of the suffix if you know these two are the same, because these will cancel out again. So you'll just be left with this thing is equal to the XOR of the entire array. So that's the goal. Here you're just checking 2 ranges, right? So you have one pointer here, and then another pointer that starts here, and then you move the second pointer along, and you consider, okay, let's have this be our first range, and then consider all second ranges. You're like, okay, if you found any that work, then you found them, otherwise you didn't. Then check this as your first range, and then consider all second ranges. And then try this as your first range, consider all second ranges, and keep going. So it's pretty obvious n squared once you see what to do. So the code, despite me getting it wrong, is quite clean. So you get the XOR of the entire array right here. If that XOR is equal to 0, this is the XOR symbol in Java, by the way. It's not very obvious, but has nothing to do with powers. It's all XOR. So if the XOR is equal to 0, then the answer is yes, right? Then you can do it. You can just split after the first number. And then otherwise, I store the prefix XOR and then the XOR of the middle part. Prefix XOR starts as just the first element, and then I add elements 1 all the way up to n. Really, this ends up being to n minus 2. And then I have the second element here, which starts as just the element in the middle range. And then I consider adding all elements up to the last element. So if this range works, then it works. Otherwise, I add the next element to the middle part. And then if there's still stuff after it, that will be j's that won't be included. And that'll be j will be the start of the third range. So I make sure the third range isn't empty that way. And then obviously, I make sure the second range isn't empty because I is the start of the second range. Yeah, so if the first range and the second range are equal, and the second range and the first range are both equal to the XOR of the entire array, that means I've found a working solution. So print yes. Otherwise, if neither of those were the case, there's no way to do it of length 2, and there's no way of doing it of length 3. We also know there's no way of doing it so that you have any number of elements in the array bigger than 3 left over, because if there were, then you could do 2 or 3. So all ways are impossible then. So the answer is no. All right, cool. That's problem B. Let's try problem C. So yeah, you want to see, you've got some array, and you want to remove the minimum number of elements possible from it so that there is no way to split the array up into 2 groups that have the same sum. What is the solution to this? I forget. I just coded it. Well, first of all, you can check if it's possible to do that initially. Yeah, here's the solution. Okay, so first, let's check if it's possible to do initially. If you want to do that, you can do this thing called a knapsack DP. So if you look up Algorithms Live Knapsack, Matt Fontaine has a great video about knapsack DPs where he talks about how you can check if you pick some subset of numbers what sum you can get. Knapsack DP does that for you. I'll very quickly go over the idea, which is we have a Boolean array, of which elements we can reach, which totals we can reach. And for each element, we can either take that element or not take it. So if we go through the array in decreasing order, we won't consider adding the same element twice. And what this does is we can just say, if you can reach, like, let's say you're considering taking an item of cost 5, right? If you can reach a sum of 12 and without taking this item, then you could take this item and reach a cost of 12 plus 5, or 17. So if 12 is true, then set 17 to true in this list of, of all the things you can reach. So that's the idea behind a knapsack DP. This will give us, like, if we pick some random subsequence of elements in the array, this tells us what possible sums those can add up to. And we do this in the maximum sum times the number of elements runtime. So in this case, it's 2 times 10 to the 7. So 2,000 times 100 times 100 is the runtime. Okay, so that will tell us if we can do it in 0 moves. Now, the key observation here is that it's always possible in 0 or 1, and maybe that's a good thing to suspect, to be suspicious of when you read the samples and you notice, hey, there's nothing with anything bigger than 1, right? So maybe you think, oh, you can always do it by removing one thing. Now the question is, how do you find the right thing to remove? So let's say hypothetically the array has an odd number in it, right? If the array does have an odd number, you should be able to remove that number, and then it will be impossible to split the array into 2 equal halves from that point onward. Why is that? Well, here's why. Let's say the sum of all of the elements is odd, right? So if you have a sum that's odd, well, if the sum of everything is odd, you can't split it into 2 halves because all of the things are integers. So the sum over 2, this is like not going to be an integer, so that won't be possible. Okay, so what that means is initially the sum has to be even. Now, if we take some odd number and we remove it, the sum is odd, so it'll be impossible. Okay, so if there is any odd number, it's impossible. Cool, we're good. Otherwise, well, there might not be any odd number. All the numbers might be even, so it might not be obvious which element we have to remove. But here's what we can do. If all of the numbers are even, we can take our measuring stick and double how long it is. So we can like use a different like currency that's twice as valuable, for instance, right? Or count every number as, we can divide each number by 2 is what I'm trying to say. And that's like a legit thing to do, because if you imagine these are line segments, right? You want to pick line segments that add up to a certain length. You can just say, well, instead of counting a unit as 1 ruler, you can just make your ruler twice as long. Everything's still an integer, you're still solving the same problem, you just have everything that's twice as small. Or I guess if you're buying things from a store that need to add up to a certain price, you just switch currency to a currency that's twice as valuable. You're still solving the same problem. You still want the same net value, it's just using a different type of dollar, right? So that's a legit change you can make. It won't change whether it's possible or not. And you can keep dividing everything by 2 until something hits a price of 1. So once something has a price of 1, then if you remove that thing, your sum will be odd. And there you go. Yep. Cool. So that's the solution to that. And here's what it looks like. So otherwise, this trailing 0 part is just it counts how many times can you divide by 2 from this number, right? So like the number of trailing zeros in the binary representation is the maximum exponent on a power of 2 that you can raise 2 to, so that this number will still be divisible by 2 to that power. So if it has 3 trailing zeros, any number with 3 trailing zeros in binary is divisible by 2 to the 3rd, which is equal to 8. And the same way that any number in decimal with 3 trailing zeros is divisible by 1,000. So yeah, this is just like some, I don't know, clever way of doing it if you're familiar with binary. And then the answer is you just find one of the things that isn't divisible by whichever thing has the smallest number of trailing zeros. Yeah, okay, cool. Awesome, that's problem C. It was a very good problem. I thought that was cool. All right, problem D, cut. So baby ehab will cut this array up into a bunch of different numbers. The question is, for a bunch of different queries, you want to pick this subarray of the original array. And now after you do that, you're going to cut it up into different ranges so that the GCD of every range is equal to 1. Now they don't tell you that. They tell you the lowest common multiple is equal to the product. But one thing to notice, it's like a math fact, is that the product of some set of numbers, or I guess the product of two numbers, is equal to their LCM over their GCD. No. Let's try this again. The product of two times two numbers, so A times B, over their GCD is equal to the LCM. There you go. What this is saying is, if you have A and B, you have to include all of the factors that are in A and all of the factors that are in B, but you don't have to include any of the factors from B that you already had in A. So you have like the factors that are in A, these are in A, you have the ones that are in B, and then these are the ones that are in both. Well, you're trying to get the LCM is the product of all of the factors in this entire grid, which is equal to A plus B minus the both section. That's why this formula is true. So yeah, so basically what we're saying is like we want there to be no factors that we share between any of the numbers. So like any two numbers in a continuous range have to be coprime. They can't share any factors. Okay, how do you do that? Well, let's say, hypothetically, for each number in the array, we knew where the next number that isn't coprime with it is. So maybe this number and this number, maybe they share some factor of 2, right? And maybe this number and this number share some factor of 5. And then these numbers share a factor of 7, for instance. Maybe you have a number here that's coprime to everything, so it doesn't matter. Now, any time that the range you pick includes this entire range, that means it won't be legal. So if we want to leave all of these numbers together without splitting them up, it's going to be impossible because these two numbers share a factor. So their LCM will be less than their product. Yeah, so we can't ever have this happening. And then this ends up being the same problem as gassing bunnies. So gassing bunnies is a super common problem. The idea is you have a bunch of bunnies, and the bunnies are on a train. So the train goes from, it's like a linear train, goes from 1 to n. And then you have bunnies, this bunny will like get on here, it'll get on the train here, then it'll travel the train for this entire range, then it'll get off here. And you want to put poisonous gas chambers to kill all the bunnies on your trains. It's a very morbid problem, but I didn't come up with the problem, but it's a great problem, and it's very memorable by the Gassing Bunnies title. So you want to kill all the bunnies, and you want to do it by installing some like gas things that kill all the bunnies at a certain position on an edge here. So you kill the bunnies here, for instance. So the question is, what's the fewest number of gas things that you need to install to kill all the bunnies so that no bunny can travel across this journey without passing at least one gassing station. Cool. So yeah, that's the idea. Now, in order to solve this problem, as well as to solve gassing bunnies, you would install the gas stations as late as possible. So when, like, if you'd start here, you'd say, okay, we looked at this bunny. These bunnies are still alive, and they end up here. So you keep going, and then you're here. Okay, these bunnies end up here. So what we're saying is, when we're traveling this way along our sweep, we have to install a gassing station at the latest right here. We might have to install one earlier, but we can't get to this element here and not have installed a gassing station. So we'll keep going, then we'll be at this element. We'll look at the things, or look at like where it would consider. So we have to install one before this, we have to install one before this. Now we get here, we're like, okay, we need to have installed one, so we install one on this edge, and then we clear out all of the concerns we currently have, right? Because all of the bunnies that we've seen from the left side are now dead. We've killed all of them right here. So now we look at this and we see, okay, the first thing to this guy's right, is there anything to this guy's right that would have bunnies that are still alive? In this case, there isn't, so we don't have to worry about it. In this case, we have another restriction. So right here, we have to install a gassing station. Like when we're at this position, we have to install a gassing station to the right of this person. When we're here, we have the constraint earlier, but we've removed that constraint from our earlier gassing station. So we don't have to install one here. And then we get to this last position over here, and then we're like, okay, well, we have a constraint, which we haven't satisfied yet, so we'll satisfy it now. We install another gassing station. So that's the solution to gassing bunnies. Not to this problem, though, because this problem has multiple queries. So what we first want to do, in order to solve this problem, is build these edges. We can do that just by saying for every prime factor in every number, when is the next number which has that prime factor? We can iterate through all of the prime factors in every number, and that'll take n log n time. And then we can store an array as we sweep from right to left. We can store an array of what's the next number which has this prime factor. So that's pretty easy. We can build these edges pretty easily. Now the tricky part is how do we solve gassing bunnies, but for a bunch of different queries? Like how do we solve each gassing bunny query very quickly? And here's the idea. We can do kind of an observation here, which is when we go from right to left, or when we go okay. So we have all of these links. In addition to all of these links, we want to say, I kind of skipped one part here. If you were to start a range here, where would you end that range? Yeah. So you have to say where would you end the range. Let me give a better example here than this one to make it a bit more interesting. So maybe you have one range that's like this. You've got another constraint that's like this. Then another constraint that's like this. And then maybe one more that's like this. Okay. So we want to say, for each number, if you start here, where do you end the range? So for this number, if you start here, your range can continue forever, right? Because if you had made a cut right before this, there are no restrictions that you need. For this number, if you made a cut right here, you would have to start the next range here. So you'd have to make a cut here. So what we can do is like imagine creating arrows to where the next time we would start a new range is. In this case, it's here. In this case, it would be here. It would be the same white arrow that it has. For this number here, it has to be to the same white arrow it has again. So it would be like that. And you might think these are all, I guess this one's over here too. You might think these are all going to be the same as the white arrows, but they're not quite. And you'll see why in just a minute. For this one, for instance, this doesn't have any white arrow outgoing from it. So it's going to be to this position here. If we had cut here, the first constraint we're going to have is going to be this white arrow here. So it'll have that link. And then this one has the same link here. Or sorry, no, just kidding. If we had cut here, we need to stop here. Now this one does have a white link, but we still want to stop here because this range is it has a smaller range inside of it, and this range is going to be more demanding. So even if we start here, we still have to satisfy this inner requirement. And then finally, this range here is going to have a line here. So we have this graph sort of thing, and it turns out this is actually a tree because everything has one parent, which is to its right. So there are no cycles, everything has one parent. The fact that it's a tree isn't really that important. But you can see that like if you're at one element and you see, okay, if I were to, as late as possible, wait for as long as possible, and then split the array, or like place your gassing station, whatever you want to think about it as. If you wait as late as possible, what is the next thing that starts the next range? And from that, you can just repeatedly wait as long as possible and then start, and then wait as long as possible and start. And that's the idea. So, yeah, so you can do that. Now, the question is, this will be like this next array. The question is, if for each power of 2, we wait as long as possible for this power of 2 and then do the next thing. So, in other words, let's say we wait for, we go as long as possible, and then we place a gas station, and then we go as long as possible and place a gas station, and we do that 10 times. Or not 10 times, let's say 8 times. In that case, you'll have placed 2 to the 3rd gassing stations, or split the array 2 to the 3rd times. So if you have that array built up in the same way you do binary lifting, then you can binary search how many splits you need in order to be able to make it to the right endpoint of your query. And that's the idea. So to summarize, first you build these white links, right? This next array. And then you build these green links, which are, if you were to start here from gassing bunnies, what is the next place you would have to split the array? Okay, so you got the green links here. And now we're going to binary search how many green links do we need to take. We can do that binary search by using binary lifting on these green links. If you're not familiar with binary lifting, there is an algorithms thread video on that. It's, I think, episode 8 on tree basics, where I talk about that. And I talk about it on trees, but this is a tree, and you can do the same sort of thing with this. Cool. All right, I'll go through the code very briefly. Yeah. So next in this case is what is the next, what like next, these are like the green links in the picture. And then next scene is the next time you've seen this factor as you do your sweep from right to left. Okay, so I build that. I think that should be pretty clear how I do it. Like I mark, or I see the closest prime factor. That is like another requirement I have to satisfy. The earliest requirement after me is what I satisfy, and then I mark all of my factors. That's all that does. Then I build the binary lifting table. This is exactly the same as what it looks like in tree basics. And then finally, I do a binary search to see how few cuts can I get away with in order to get to the right pointer here. Really, I want to say get one past the right pointer. So I try the biggest power of 2. I say, if taking this many steps would get me too far, then I take 1 fewer power of 2. So this whole thing, even though it's got 2 nested while loops, it only runs in log n time. Cool, that's the answer. Yeah, there's other stuff here too. Okay. All right, last problem is problem E. And I won't show code for that because I don't have it fully working, but I can give you some general idea here, I think. And then, I guess, keep me honest in the comments if I'm totally wrong. So, in this problem, you have a bunch of cubes. You have a very large number of cubes, up to 1 billion cubes. And you have a parameter k, which is the number of inversions. Not inversions, just kidding. The number of swaps that you're going to make. So you're going to make this number of swaps, and you want to say, after making this number of swaps, how many different permutations could you reach? So obviously it's really big, so you print the answer under mod. But like what this number is a bit tricky, and then also like you have to answer it for everything between 1 and k. I don't think that really makes the problem any harder. The hard problem is just answering it up to k, and then you like speed up your runtime a little bit, but that part's pretty easy. The hard part is the math. So let's think about it for a minute. Now, an important part of the problem is that, which I missed for like an hour, is that the things you swap don't have to be adjacent. They can be any 2 elements in the array, which I think makes it quite a bit easier. But let's look at this for a minute. Let's say you have some permutation like this, and first you swap these 2, and then you swap these 2. At the end, what will happen is you'll have a cycle in your permutations. So you'll have this one should be here, this one should be here, and this one should be here, I think. Or it might be backwards. But you have a cycle of length 3. So yeah, it would look like this. 1, 2, 3. In other words, this is a 1, so you draw an arrow to position 1. This is a 2, you go to position 2. This is a 3, you go to position 3. That's what I mean by cycle. So you have a cycle in this permutation, and this cycle of length 3 took 2 moves to make. So like the cycle size minus 1 is the number of swaps it takes to make that. Yeah, okay. So the next thing is if you have like some cycle and then you have some other cycle like this, if they intersect, then this just makes one big cycle. So I'm pretty sure then you could have just gone like this, right? So we're not going to count 2 cycles if they intersect. Now, that might change your answer because you can have a cycle and then undo the cycle. So you can skip any even number, right? If you have to make exactly 10 moves, you could make exactly 8 moves by swapping the first 2 and then swapping them again. So we have to consider that, but we'll do that at the end, and that's pretty easy. So now the question is, if we're going to pick disjoint cycles, and each cycle has a cost of like k minus 1, how many different things could we pick? In order to do that, we could do some DP. So let's say we do a DP where we store, we can store like how many elements are left. We could store how many swaps we have left. And then we could also store the current cycle size. So what I mean here is the number of elements here is, like, you might think, oh, there can be up to 10 to the 9th elements, but you never remove more than 200 of them. So you can really store like the number you've removed. So this is really 200, this is 200, and this is up to 200. And then once you've done this, you have to brute force how many cycles you take. So the observation here is that the number of cycles you take is at most n swaps over cycle size. I guess really it's cycle size minus 1. But the key observation here is that in total, this will be n log n. So it won't be that much. This is going to be, yeah, n times log. Because cycle size times number of cycles is less than this. So it's like n over 1 plus n over 2 plus n over 3, which is at most n log n with some integration tricks. But I won't worry about that at the moment. Yeah, that's the idea. So brute forcing the number of cycles should be fine. You just have to do it fast then. So then doing it fast shouldn't be too hard. Actually, yeah, you've got 2 seconds. Your runtime is going to be 2 times 10 to the 8, I think. Or wait, will it be bigger? Oh, it's 10 to the... Oh, 1.6 times 10 to the 8. Yeah, so you should be fine. And the log is even smaller. The log is like log of 20, so it's, yeah, it's even smaller than that. So it's like less than 10 to the 8. Should take less than a second. Shouldn't be too bad. Yeah, so now the question is, like, if we know all of these things, what is the runtime of doing this? So here's the idea. We have a bunch of elements. Like the counting part we have to do now is we have a whole bunch of elements. And maybe we have to pick like 3 cycles of size 4. So for the first 4 elements, we're going to pick any 4 elements here. And the order of these 4 elements is important. So yeah, like the order matters. And then we have another 4 elements, right? We pick another 4 elements. Maybe there are these 4 here. The order of those 4 also matters. However, the order doesn't entirely matter, because when you have this cycle here of 4 elements that you chose, these first 4, you can pick any starting point. So the order of the cycle matters, however, the starting point doesn't matter. If you understand what I mean there. So like, yeah, the order kind of matters. So we want to divide by 4 because there are 4 starting points, but the order still matters. Okay, then we have the second cycle. Here we divide by 4, but the order still matters. So yeah, so it's like we multiply by 4 factorial divided by 4. Okay, in total, we know how many elements we pick. So we have n elements, and we choose k of them. So there's like some n choose k. Then we want to multiply by 4 factorial to the power of however the number of things here, the number of cycles, n cycles. And then we want to divide by 4 to the power of the number of cycles. You can combine these and then instead just multiply by 3 factorial to the number of cycles. If you want to get rid of these, then you don't have to do division. So now you just have n choose k in this. Then you might be saying, but David, n choose k is really hard because n and k are both huge. But it's not, because you can do the naive n choose k by expanding it. So if n is 10 to the 9, then you have like 10 to the 9 times 10 to the 9 minus 1 times 10 to the 9 minus 2. Let's just do n choose n minus 3 divided by 3 times 2 times 1. So yeah, it's just equal to that, which you can evaluate in order k. Okay, now you might be saying, but David, if we're evaluating that in order k, don't we have to add k to our runtime? No, we don't, because before we do any of this, we can pre-comp all of these n choose k, because n is always the same, and k is always going to be very close to n. So we can pre-compute all of these, and then we can store them in an array. You might be able to store them in a hash map, but I would be careful with that, because then you have overhead with the hash map lookup. Yeah. And then on top of that, that sole solution might be wrong, but I think it's right. It feels right. Or at least it feels close enough. Okay. Yeah, that's all from me. Hope you enjoyed the round. If you beat me, well done. Well done. And if you're free this weekend, feel free to do the Ludum Dare. It's from Friday to Sunday in Pacific time. But I guess depending on your time zone, it might be some other time. But it's a great way to practice doing fun stuff, especially if you like playing and making video games. I guess, are there any important Codeforces contests over the weekend? No. There's one Friday morning, but it won't conflict with Ludum Dare, so definitely worth trying. All right, thanks for watching. Have a great day. Let me know if I missed anything in the comments. And good luck on the next contest. See ya.